Let us reintroduce homology and cohomology. So first you have this chain complex or a sequence of free groups Ci plus 1, Ci, Ci minus 1 and so on, and you have connecting homomorphisms or boundary maps delta I plus 1, delta I and so on. So first you apply delta I plus 1, then you apply delta I, you get 0. So this was the condition for the chain. That means that image of delta I plus 1 lies in the kernel of delta I. So we also write this condition as delta square equal to 0. So let us draw some pictures. So say you have Ci here and then you have Ci minus 1 here. So this is Ci minus 1, this is Ci. Now the map delta I acts on Ci and it takes this rust color portion or yellow portion to 0. So this becomes kernel of delta I. So this is the map delta I. This yellow portion is the kernel of delta I. Then you have this free group Ci plus 1 and delta I plus 1 acts on it. And it maps it inside the kernel of delta I. So that is our condition. You first apply delta I plus 1 and then delta I, you get 0. So the image of delta I plus 1 is in red and it lies inside the kernel. So the homology was kernel of delta I over image of delta I plus 1. So that is nothing but yellow modulo out the red in the free group Ci. Now in cohomology we just reverse the arrows. So I'm going to write the chain complex with the subscript as a superscript. So you have arrows going from Ci minus 1 to Ci plus 1. And here the maps we will write as di minus 1, di plus 1 and so on. Again first you apply di minus 1 and then you apply di, you should get 0. So this you can rewrite as d square equals to 0. That means image of di minus 1 lies in kernel of di. So you can have a cohomology groups, that is kernel of di over image of di minus 1, and you can draw a similar figure associated with the co-chain complexes. So we call kernel of di as co-cycles and image of di minus 1 as co-boundaries. And in homology we have kernel of delta I as cycles and image of delta I plus 1 we call boundaries. Now we want to obtain cohomology from homology. So in homology we have a chain complex and in cohomology we call that chain complex as a co-chain complex. So let us now obtain this cohomology from homology. So first we just copy down the chain complex from the top. And say you have integers as z. So you have the boundary maps. Now you have these group homomorphisms from these free groups Ci minus 1 to integers. So you call this phi I minus 1, say this you call as phi I and this you call as phi I plus 1. Now each of these triangle commutes. So first let me write this down. Phi I is nothing but a homomorphism, a group homomorphism from this free group Ci to integers. And each of the triangle here commutes. So what we get is phi I is equal to, first you apply delta, then you apply phi I minus 1. Similarly for phi I plus 1, first you apply delta, then you apply phi I. Now this you rewrite as d I minus 1 of phi I minus 1. So that is d subscript I minus 1 takes this map phi I minus 1 to phi I. This you redefine as di of phi I. So di takes phi I to phi I plus 1. So here you can write down now phi I minus 1 as part of ci minus 1 phi I and then phi I plus 1, and di takes phi I to phi I plus 1 and di minus 1 takes phi I minus 1 to phi I. Now if you first apply di minus 1 and then di to say phi I minus 1. So this is nothing but you first apply delta and then phi I minus 1, and this now you can put a delta behind this. Phi I minus 1 delta composed with delta, then another delta. So this is delta square, which is 0 from our definition in homology. So phi I minus 1 acting on 0 will give you 0, because phi I minus 1 is nothing but a group homomorphism. So you have seen that d square is 0 and you have gotten a complex. So you can define cohomology groups. Now just a remark, d phi 0 means that phi of delta is 0. That is, this group homomorphism map vanishes on the boundaries. Now we want to link up this homology and cohomology. So linking up homology and cohomology can be done via the universal coefficient theorem. So this universal coefficient theorem states that this cohomology of the chain complex, you can represent it as home of homology groups to integers, that is homomorphism from homology groups to integers, and you do direct sum of it with X homology group one dimension down to integers. Now we have not defined X, but you can think of X as a black box for now, and some of its properties are X of a direct sum b comma z is X of a comma z direct sum X of b comma z. So X of a comma z is 0 if a is free. So in particular X of z comma z is 0 where z is integers, and X of zn comma integers is just zn. So zn means z modulo nz. Now we have used integers everywhere, so we could replace these integers with any group G and everything we have said above will hold.